sore. Good afternoon, everyone. Selamat sore. Good afternoon, everyone.
Good afternoon, ma'am.
Okay, so let's continue what we have left on last week, right? Thursday last week. Okay, so we were here. And we finished with the first order system, and how to find the testing sign and also the rise sign for the first order system. So where were we? So we were here, finding the right sign and also finding the settling time for the first order system. Right, so for the first order system, it is different than the second order. So in first order system, there are only few properties. Few properties mean mostly there are only rise sign and settling sign. We don't have other properties than this. And finding the rise time and settling time for the first order system, we can immediately use this equation. For the TS or settling time, we can define it 4 by A, where A is the pole, the location of the pole, and CR is the rise time, is equal to 2.2 by A. So A is simply the pole that you find it from the transfer function. Okay, this one and also this. You can find this in the book. So now if to that if you have a transfer function, so if you, let's say, it is simply like this. So this is your transfer function here. We call it the TS. Okay, TS, so don't be confused. And here is our input, RS, and here's our output, or yes, right. So when you solved the problem that you learned last week or a couple weeks ago, so you get TS, transfer function here, is simply the output divided by the input. Okay, the output here divided by the input is our transfer function. This is what we solved previously. Okay, and what is inside the box here, we call it as a GS. This GS. or simply if you want to get, this is not for today's topic, this will be the next topic. But it is just to tell you that GS is different than TS. TS is a transfer function, and GS is simply a transfer function of one block. Okay. So here it is to tell you that's the difference. So the step response, when you call it as a response, it means an output. This is output. Okay. This output can be CS or YS or any other notation. Okay, so the step response is this way, which is K divided by S plus A. And here it is, the S is our input RS. So the transfer functions, if you take a look the time response, how it responds to the time, and also the output, how the output behaves with respect to time. This graph is a first order system, so you have to keep that in mind. So the vertical axis here is our output, okay, and the horizontal axis here is our input. So now from the test, the final value is around 0.72. So from here, what do you think is the final value? Of course, the final value is when t goes to infinity, and this is our t goes to infinity, and here is around, this is what we call the final value, our final value. So from testing, the final value is 0. Approximately, okay, the symbol is approximately. Approximately 0.72. Time constant occurs at the time when the response reaches 63% of the final value, which occurs at approximately 0.6. And 1 by A is this, so A is the pole, is our pole. And remind yourself again what is pole and what is zero, right? And here we have A equal to 7.7. So the first response has a final value of K by A is 0.72. So K will be, what is K? K, if you take a look here, the transfer function and the rectangle. So here it is, our output. Our output here. So K is here. K is usually called as gain. Okay, right. So K is let's go right here at the bottom. So K is equal to 7.7. Okay, and the question is, what is the final transfer function? Because we want to find what is the pole, what will be the pole, and what will be the zero. In this case, our zero is our K, or K. So from the test, from the experiment, they found out that K is equal to this, and A is equal to 7.6. So is there any questions for the fifth order system?
Not yet, ma'am.
Yeah? No?
Not yet. For me.
Okay. If there's no questions, let's continue. Let's continue with the second order. So for the first order, it is quite simple, and the properties are very few, only few properties for the first order system. But for the second order system, you will need many properties. We have what we call it as a damping ratio, and also here we have a natural frequency. We have also damped natural frequency, and some angles and stability and so on. In the second order system, we call it as a second order. Of course, the denominator, or what we call as a characteristic equation, so you have TS, you have the numerator, right? The numerator, and this is the denominator. Okay, so if in first order system, you have it simply K as plus 8. So this the power of the denominator is only power 1. That's why we call it a first order system. For the second order system, you have more than 1. We call it as a second order, so the power is s power 2 plus a s plus b, for example, like this. Okay. And it can be anything from k to k times b and so on. Right, so the denominator, this one, we call it as a characteristic equation. Characteristic equation. Right? So you have to be familiar with many terminology by yourself. You cannot rely everything on the teacher. You are not in high school anymore. You are in university. Well, 60–70% you should be independent by yourself, and 30–40% we will give it in the class. That's the definition of a university, that you get more freedom in learning something. So this, we call it as a characteristic equation. You have to understand that when the question asks you to derive it, let's say, what is the characteristic equation? Can you find the poles or the roots of the characteristic equation? It means it's not the whole equation of transfer functions. It is only the denominator. Okay. And here it is, our second order system. And in the second order system, the function or the model, the mathematical model that you should always keep in mind, many students forget this, always forget, is this. So let's say if you have chances divided by not 100 but 200, and this is 2x squared plus maybe 8s plus 200 like this. For example, you have this kind of transfer function, and find what is omega n, or natural frequency, you knew this term, right? Natural frequency in the class of vibrations, mechanical vibrations with harus or wiwi and so on. You know this natural frequency means now what you have learned is what you have to learn is damping ratio. Right, so let's go back to this equation. Now, from these equations, find, for example, find what is zeta. This is symbol, we call it zeta. Okay, pay attention, your ear, your eye. After so many classes, it happens after so many classes. And if you know me, if you were in my classes before, I always ask students to come to the front to work on some exercises, right? If it's not online like this. And students will call this as a epsilon. This is not epsilon, okay? This is zeta. The way you call it is zeta. And that upsets me. Okay. And this we call it as a zeta. This is a Greek letter. Okay, find what is zeta, what is damping ratio, what is omega, and so can you find it immediately with this form of equation? No, you have to make it exactly like this way, which means the coefficient of s squared should be 1. Then you will have s squared plus for s plus 100. Okay, and this becomes also 100. Right? So now after you change it to be this form, you can find what is zeta, what is omega. That's the way you solve it. And I'm showing you this so that you do not repeat the same mistakes again, from generation to generation. This is the form that you should always keep in mind for the transfer function of a second order system. So here is the S square, which defines that this is the second order system. Then this is 2 zeta omega n. This is our coefficient, S power 1. And here is the constant omega n square. Okay. The natural frequency, okay, so the natural frequency is defined by the symbol omega n. Okay, the natural frequency will tell you what does it mean physically. And you have also a damping ratio from the name damping. So if you have a function of your output, let's say your output is never stable, it's always like this, oscillate, it always oscillates. So this there is a ratio for doing this. We call it as a damping ratio. And at t equals to something, for example, like this, at t equals something, then it becomes steady. Then this is also there is a damping ratio that on the name damp, it works as a damper to stop this oscillation movement. Then we call this as a damping ratio. Other than damping ratio, we have also omega d, damp natural frequency. So those two are different things. We have omega n, we have omega d. So those two are different, right? Omega n and omega d. So these three are the properties There are still many other properties. So the way you write the transfer function is this. The s square here should be with the coefficient 1. And the s here, the coefficient becomes zeta omega n s plus omega n square. Okay. This is the most important thing you should know. Okay, so from these properties, we have zeta, omega n, and omega d. Then if we bring it back to the x-plane, you remember this, this is what we learned on Thursday. You know now how to draw the axis, the horizontal axis here, we call it real number, right? And the vertical axis here, we call it as a imaginary number. Okay. So J defines the imaginary part. So omega here, okay, this is what is not written. Omega here is not omega n, but J omega c. So the way we find what is the value is equal to this. So here is our J omega, or simply J omega, omega t. So here is our J omega. So what is omega d? Omega d is a damn natural frequency. It is not equal, it is not the same as omega n, right? So you just keep that in mind. So omega d can be found from this. This is omega d. Omega n, square root of 1 minus zeta square. Okay. And now this is for the imaginary part. All right. So we know the imaginary part contains the omega d. How about the real axis, sigma? Real axis is composed of this one. Let's take a look on the left side. Minus zeta times omega n. Minus because this value and in the left half plane, this is L half P, LHP, sorry, this is RHP. In the left hand plane is minus. So it is actually simply zeta times omega. Okay. And now what is omega n? So if you have poles, let's say I cannot get any random. I cannot get any random value, but let's say s squared plus 3s plus 17 maybe, right? This is our characteristic equation. So here at the top we can say 70. That's fine. Okay. So now if you factorize this, then it becomes for example, okay, this becomes complex. So this becomes plus 2 plus 2j, okay, for example, like this, s, okay, all types of this. And this becomes the counterpart s minus not still plus 2 minus j. Okay? So the factors are complex. So you can plot it here. All right, so this is the pole, this complex pole. Okay, this one we call it as a complex pole. At the top and also at the bottom, because there are two factors. There are always two factors. Why? Because this is second order system. So you will have two factors. Okay, so in the complex pole, if it is a complex pole, definitely you will have imaginary part. If you have imaginary part, you have omega g. That's for sure. Okay. And the real part is here. Okay. The imaginary part, and this is the real part, and also the imaginary part. And if you take a straight line from this, what you call this, from origin, okay. So if you take a straight line, the diagonal line from the, here it is, we call this the origin, to the complex pole. So this diagonal line is omega n, our natural frequency. Okay, and from this omega n to this is simply trigonometry, and very easy. You have an angle. Okay, this is clearly in the title. It's a complex pole. Complex pole for second order. Okay. Now the combinations of the S equals to A plus DJ. Okay, so the combination of a complex pole of a real number plus, let's say, EJ. You know that here is what you call it as a sigma in the S plane, and D here we call it as an omega T, right? Sigma and omega T. And sigma is zeta omega n. Omega T is what is that? Omega n times sine 1 minus zeta. Okay, now the combination of this complex pole, you can take a look how it affects the output in the time response. So the output in the time response, here this sinusoidal oscillation generated by the imaginary part. Okay. The omega G makes this oscillation cycle. Okay, and then the decaying, you know, from one peak to another peak to another peak to another peak, and finally it's gone. That's because the real part. That's because the real number. Okay. That's because the real number. If you have an output, let's say we draw it in the time function. example like this. Okay. So this oscillation is generated due to the omega t, and how this peak, the peak from one peak decaying, decay is also reduced or decrease. So from one peak to another peak, it is decreasing to another peak. That's because the real part. Okay, that's how they affect your output. Now let's see the classifications of the system, the second order system. Second order response as a function of the damping ratio. The damping ratio is also important. It makes your system fast respond, but you will have more these oscillations. And if we get rid of, if we delete this damping ratio, your system will be a bit slow. For example, I always use AC as an example. If I turn on my AC to be 20 degrees Celsius, if my AC doesn't have a damping ratio, it will reach 20 degrees in a couple minutes, quite long. Okay. So let's see what does it mean and how it reflects within this graph. So we have several classifications. Classification number 1, classification number 2, classification number 3, and 4. Okay. If you don't have a zeta, you don't have a damping ratio, you don't have a damper at all, what will happen? Your system will always oscillate, right? Because you don't, in Indonesia, there is no damper or quarter jump, right? So the system, it will go up and down until T to infinity. This is, we call it as an undamped force because zeta is equal to 0. The system will always oscillate like this. Do you want it to be like that? Of course not, right? When you have an automatic door, you want the door is always open, opening and closing, even without the people surrounding it. Of course not. Okay, and next we have zeta between 0 up to 1. So zeta is a value from 0 up to whatever the value up to infinity. The zeta from 0 up to 1, there's no equal here, so pay attention. 0 up to 1. So here is the case when you have complex poles, okay? All right, so I forgot to tell you. So in the case of undamped, because you don't have zeta, right? Because here, zeta times omega n. If zeta is equal to 0, so there is no real component, right? There's no real component. So what you have is only omega d. Omega d here. Now we continue to this. This is what we call as an underdamped. Zeta is in between 0 up to 1. You have both real number and also imaginary number. So your pole is a complex. It's a complex pole. Okay. These are complex poles. So in the complex fold, you have zeta. You have also omega n. So you have a complete property. So your system will look like this. This is what we call as an underdamped. So your system will oscillate quite high, then it will decay. It will oscillate again, but a little bit and down, and finally it will reach stability. This is, we call it as a underdamped. In some systems, they like to make it to be underdamped because, as I told you, it's quite fast, but it still has this oscillation movement. And the next category is zeta equal to 1. In zeta equal to 1, zeta is exactly 1. We call this as a critically damped. So in zeta equal to 1, you have a twin factor. Okay, the factors are twin, zeta, omega n, and it doesn't have omega d. What happens if you don't have omega d? You don't have an oscillation, right? You don't have an oscillation, and this one is called critically damped. You don't have this one. So it is simply going and reaching the output. It looks like more first order system. It looks like the first order system. Okay, and the last category is when zeta bigger than 1. It could be 2, it could be 3, or any number. Okay, when zeta more than 1, so you have real factors. You have real force. This is what we used to solve in the previous classes with partial fraction expansion, like this expansion. You always have this two factors real. When you have this and you don't have the omega d, you don't have the imaginary part, it's always the same. It looks the same. It looks like the same, but it is not. It looks like the same between critically damped and also the upper damped. So there's our critical damped, and here's the upper damped. Okay, you can notice the difference immediately. That in critically damped, will go slightly to the right, this and this, but this one it will go a bit straight up, and finally it will reach to the output. Here is the example with some values. So it will be clear for you. So 5, how many systems? 4 systems. So there are 4 systems. Okay, then you have been given this transfer function at the top. Okay, you have been given this at the top. I think this one is taken from the book, so you can learn it from the book as well. So you have been given this, the general transfer function s squared plus as plus b, and the numerator is simply b. Now let's replace those a and b with some values. Okay, now this is s squared, so the characteristic equation now is s squared 9s plus 9. What is zeta here? So zeta. You know how to find it? Right? This one is, you always count from here first, then omega n is 3, right? Then you have 9 is equal to 2 zeta omega n is equal to 9. Put omega n as a 3, so you have 9 is equal to, sorry, zeta is equal to 9 by 6. So zeta is equal to 9 by 6. 9 by 6 is 1 point something. It is more than 1. This is how you find it. Is it clear? Yeah. So, so from here, we know that zeta is zeta. From here, zeta is 1 point something. Or you can simply, so there are two possibilities. There are two methods. First, try to find what is the value of zeta and or factor it. So find the factor. But I think after you find what is zeta and omega n, you can also find what is the factor. Right? Because the factor is S equals to zeta omega n plus minus k times omega t. Right? This is the factor. This is the pole. Okay, so the case number 1 of B, the one thing I did it for you, I found it by using zeta. The zeta is 9 by 6. So we know it that this is 1 point something something. So this is definitely of a damped system. Okay. So if we are trying to find what is the pole, let's say find the pole, you should know how to find it immediately, right? Because omega n is equal to 3. So here's the poles. The poles are all real. So our time response, this is time response. You have two responses. Don't be confused. You have time response and you have constant. What we are learning here is an S domain. We call it as a constant. Time is in T domain. Okay, so the graph here is a time response for of a thing. Okay. Now, how about case number 2, C? The case number 2 is here, and omega n is 9. Okay, omega n is 3, right? And zeta is, what is zeta? Zeta is 2 by, so 1/3. Am I right? Yes. Zeta is 1/3. Zeta is 1/3, so definitely this belongs to underdamped system. Okay, and you can also from here find what is S1, what is S2, pole number 1 and pole number 2. And this corresponds to S1. This corresponds to S2. And your time response function will be this. Yes, because you have zeta and omega n at the same time. Okay, now let's continue to case number 3. Case number 3. So in the case number 3, you have zeta. You can spot it immediately. This is simply mathematics, very easy. Case number 3, omega n is 3, zeta is 0, right? Zeta is 0. Because from this equation, you can simply find it. So if zeta is 0, your system will always oscillate. It will always oscillate up to infinity. Okay, and the last one here, case number 4. What is omega n? So omega n stays the same, 3. And what is zeta? Zeta is 6 divided by 6, right? 6 divided by 6 equals to 1. So this one is critically 10. So you have to definitely twin factors. Okay, is there any questions?
Not yet, ma'am.
Okay, thank you. So we've seen the we've seen the second order system, its classification based on the value of damping ratio. I will continue a bit with one example. Then I will stop, and I'll talk about a little bit about the twist on the Wednesday. Okay, I will continue to the time response, function response, and let's see some examples. Okay. So from previous category or classification, now you know that there are 4 categories or 4 classifications. Okay, and second order system is finding the zeta or damping ratio. There is a formula for all of this, or how to find the zeta, how to find the omega n. We'll find it later on. And you know that there are underdamped. This is when zeta in between 0 and 1. And damped, there is a damped, there is undamped, zeta equals to 0, and critically damped, zeta equals to 1. This is when zeta more than 1. Okay. And if we compare, let's say, with the same omega n, right? Previous cases, the previous slide, all omega n is always 3. The only thing which is changing is zeta. Zeta is 0, zeta is 1, and so on and so on. Okay. So if we compare all four the time response graph, this is how it looks like. Okay. So we know that this always oscillates, this graph. So this is, we call it as an undamped. It's a redam, right? In Indonesia, in Bahasa. And next, for the underdam is zeta between underdam here. Underdam, you see that there is a peak. Okay, it depends how big is the value of zeta. If zeta is 0.9, so you will have less mountain, you will have less peak. Okay, that is, your zeta is equal to 0.2. So of course your graph will have more peak. Like this. So as zeta increasing 0.5, 0.9, you will have less peak. Okay. That's of course because you are reaching the critically dense system. Okay, here is our underdam. What is the previous value? I forgot the value, but here I suspect that it is very close to 1. It is around 0.8 or 0.9. Because by seeing this, there is only 1 and very short, and there is only 1. And now, what is the difference between upper dam and critically damped? Right, you can see it here. In upper dam, it is very, very slow. Okay? It is very slow. It is increasing, reaching the output, but very slow. Okay, probably the output is around this value. For critically, sorry, for around, yeah, for this value, let's say around 1. So for both underdam and critically damped, they already reach the output, the reference value at this time. But for overdam, because it's too damped, okay? So it reaches the output probably around this time. So overdam is quite slow in reaching the output. Underdam, critically damped, well, you can't see the difference here because it looks like for the underdam zeta is close to 1. 0. I think 0.8. Okay, so you see how those systems behave as zeta change. Right, now let's focus on, this is what I told you, let's focus on only underdam. When you change zeta, how this oscillation change. Okay, and we start from zeta with the smallest, 0.9. You know that when zeta is equal to 0, you will have this oscillation. So when zeta is 0.1, 0.9, 0.1, when zeta is 0.1, of course you will have this very high oscillation. Then it will go down, but it will go up again, it will go down again, and so on. Okay. As you increase the value of zeta, you will have less peak. we have less value of x. This is 0.2, 0.5, 6, and 8. Okay, so before I think around 0.5 as the before example. As you increase zeta, the value of this peak will decrease, and you will have less number of peaks. If we have 1, 2, and 3, and maybe there are more, 4 maybe, right? If you decrease zeta, the peaks will also less. So this is the difference. Now, in physical meaning, right? That's the physical part. You know, and have you ever joined the defense? You know, defense sidang. You should try to join one at a time, not one at a time. Sometimes defense with S or with C. Defense or sidang. It's good for you to just to attend, just to see. Okay, this is the question and this is what it means. Okay. It's good to see so that you will understand what they will ask. So in sidang or defense, they will ask more about physical meaning. So if you talk too much about mathematical equations, they will ask you about physical meaning. The same, if you talk only about its physical meaning, and if, for example, I met students, well, I was one of the examiners. Students said, we make it bigger so that the moment here will be less, the moment there will be less, like that. Okay, can you make the equation of that? So if you talk too much about physical meaning, they will ask about mathematical. This is typical in all defense of students. So you have to balance your capability of both, your understanding, your sense of physical meaning, and your sense of equation. How this equation in real life? What does it mean in real life? That's yeah, as I told you, it's good for you to attend one sidang in the end of the semester, not for understanding the topic, but to know what will be the question. That will be good. And there is a question just to share. You know, I just talked 1 hour about the topic, so I will tell you something else. Icebreaker. Okay. There was one student studying about a car. Thesis, not thesis. Tugas akhir or final project about a car. Okay. A simple question is, okay, so this car is moving with some velocity to the right, and it has a drag force, it has this kind of force, friction, and so on. It has the normal force, blah, blah, blah. And one simple question is, where is the direction of the inertia force? That's a very simple and basic question. And he didn't know. And he didn't know what is inertia force. How it is, what is it in mathematical equation? What's the equation of the inertia force? What is the direction? That's the simple question. After he talked too much, then the simple question is, what is the direction of the inertia force? And how your equation looks like, and so on and so on. Right, that's to give you, you know, the image that physical meaning is important and mathematical equations are also important. So let's go back here. So what does it mean between zeta 0.1, 0.1, 0.1, 0.2, 0.3, 0.4, and so on. Okay, so what does it mean in real life, in physical meaning? Well, it's simple. Just by seeing this, if you have, let's say, if you have a navy, yeah, if you have a navy, if you have an AC, does it look like an AC? Yeah, just imagine this is an AC. If you have an AC, in the beginning, if you set it as a 20 degrees, right? You want it to be 20 degrees. And this AC works in the ambient temperature before. So the environment, ambient temperature is around 30, Surabaya today, around 30 degrees. I don't know why my pen works this way. This is a new one. Okay, 30 degrees. This is our ambient temperature. So initially, this AC, it doesn't work, right? It is off. So it starts from zero. Starts from zero, and if you put zeta is equal to 0.1, so your AC will start from zero, and it will go more than 20 degrees. Okay, let's say this one is 20 degrees. It will go far away, and it oscillates. So your system takes quite a long time. It goes up and down. 20 degrees, it goes to 25, then it goes below to 16, and so on. And finally, it will reach 20 degrees. It takes such a long time. Your system oscillates too much. So for mechanical in physics, for mechanical parts in physics, I mean in physical, for mechanical parts, this is not good for your part, right? Because you have too many oscillations, it goes up and down too much. So you increase your zeta to be 0.5, let's say, in 0.5. Okay, in 0.5, I will reach quite high. That doesn't matter. Higher than 20, but it's not too high. Probably around 23. Good. But I will not oscillate too much. Right. So this one fits my system well. So I will choose zeta 0.5. So this is the physical meaning of the zeta, starts from 0.1 up to 1. Is there any questions? So before coming to the next, so there are several properties: peak time, so settling time. There is also settling time for second order. So let's see an example here with value. Here is an example for understand. Okay, we understand. We will talk a lot about understand system because the system is interesting. So that's why we'll talk about underdamped system. So in the underdamped system, for example, like this, take a look at it. We have this transfer function here. So if we write it down as a s square, just 2 zeta omega n. So here it is. So s square has already 1 as the coefficient. So we don't bother to make it as a 1. It is already 1. Okay, so from here, it's quite simple. What is delta and what is omega n? We know it that omega n is equal to square root of 200. What is it? It's n. Is it k? Right? And what is zeta? Zeta is 10 divided by 2 times 20 square root of 2. Okay, so here we have square root of 2. Am I doing right here? This one is may correct me if I'm wrong. Okay, this is zeta, this is omega n, and you can also derive the factors, or if it is too difficult, you can do it as I told you. So S1 is zeta minus plus, no, if you put it as a equal, then it becomes minus zeta omega n plus j times omega t. And pole number 2 is minus zeta omega n minus j omega t. Right, so you can find it either factoring it. If it's too difficult for you to factorize it, so you can use also there are many possibilities. There are, I used to call it when I was in high school, rumus ketchup, ABC, right? Minus b plus minus square root of b square minus 4ac. You can also use this. Well, there are many possibilities. I don't have to tell you this. Okay, so you find the pole. Here is the complex pole, S equals to minus 5, J. Pay attention that we have plus minus here, okay? Plus minus of the imaginary part. So minus 5 is the real component, the complex pole. Okay, it shows how the response decays, time constant of 6k. Okay, and the damped oscillation is the imaginary part, which is omega t. So omega t is this. Okay, and if you take a look again, the S plane, the S plane looks this. I will draw more in the left or in the negative plane with our j omega t, j omega t, and you know that this is minus 5, and here is 13 something, positive and negative. There are 2 poles. Okay, so here is our pole, right? And here is our omega n. So other than finding it from the transfer function, let's say transfer function is not given. There is no transfer function. There is only s1 equal to 5 plus minus j 13. Find 2, 3. Find what is zeta, what is omega n from here. Right. So you plot what is minus 5 is here. You plot the imaginary part here, 13, and minus 13. Okay. So zeta can be found from cross the tangent inverse of the imaginary part divided by the real part. Okay. It is the expression. Now you have to understand again. So what is this angle actually? Because there are cos and also tangent. So what is the angle of zeta here? So what does this mean? Okay, so we'll stop here for the second order system. We already learned about underdamped. We learn next week on Monday. We learn about more properties. There are settling time, peak time, what is overshoot, what does it mean overshoot, and how to find it, and so on. We learned this on Monday, and we'll stop here for the second order system. And please keep in mind that the second order system will not be in the quiz. The quiz will be only until finding the free body diagram, finding the transform it from, let's say, you will be just given the questions will be it is connected one to another. So you will be given only like this. I will give you an example. Yeah, it can be a combination between translation and rotation. So pay attention. I think we did this before. Let's make this one. Okay. This is the one that has been solved by your friend. And one, right? Yeah, for example, you will be given this only. And the questions can be many things from here. For example, find and the one solved by your friend, it was still in symbolic. Symbolic means I didn't give you what is the value of M, what is the value of P1. So you should pay attention for that. Okay. And the homework solved by your friend, everything is symbolic. Okay, so K1, M, in the quiz, we'll give all the values. M can be something, and what else? K can be some values. This is also can be some values. Okay. So finally, if you remember the questions of this exercise, which has been solved, it was, what was it? Theta, right? Theta by the output, right? By the output. That's defined by output. Something like this: input, output by input. So this is our transfer function. And you had it before. Everything is in symbolic. You can find it. This is this. But now, if it has value, let's say this one is 16, this one is 10, and also K1 is 9, and so on. So now, what is the theta as a function of T? The next question will be like this. So you should be able to, if it is a second order, so you should be able to factorize it so that you can apply the partial fraction expansion, right? So you can apply partial fraction expansion after you factor it as power something minus something or plus something. After you apply this partial fraction expansion, so that you apply the Laplace, now you can find, let's say, 1/3 minus e, like before, minus e plus blah blah blah. So the questions can be like that. So this is the picture. Find. There are many. First can be find what is SPD. Find what is that, and then FTD. Find what is the transfer function. Okay. Find what is TS. Can be also both output, XS, and what is T, and so on. So if all these values are given, means this that you found, you should substitute all the values. The values here are given. You should substitute all the values. It cannot be in symbolic anymore. Right? So that will be the quiz. I think for the last 3 years, the quiz is always the combination of both translation and notation. So you should learn both cases, translations, and rotation. The quiz will be at 1:30, okay, 1:30 on Wednesday. There are any questions? Okay, I will share the code of today. Oh my God, is everybody here? Oh, yes, I know. Yeah. Oh, yeah. And like usual, as usual. For example, if you are given a time for working on your quiz, let's say 100 minutes. So you will be given 100 minutes for working on it. And then we'll give you around 15 minutes for uploading your answers to. If, for example, in case there is a bad connection for you, but usually I always receive all the answers to. In case if there is a bad connection, just keep trying to submit it. Usually, if you are late about 5 minutes to 3 minutes, up to 5 minutes, I'll be fine with that. Because I found students, they submitted 2 hours late, then that's different case. Okay? 1 hour late, 2 hours late, that's different case. I will not accept that. If you're late in submitting it due to the connection, 5 minutes late, for me, that's fine. All right, so this is the code for today's attendance for my class. I don't know for Bamba, you need to ask them directly. Okay, please please attend the quiz. It's going to be difficult for me to find time to replace in case you are sick or whatever that might happen. I hope not. But please be present in the quiz. If you have to replace it, let's say you cannot attend and you have to replace it, it's more difficult for me to find time, because if I go to I have a training even until Saturday. Okay, right, that's it from me. And even though we'll not meet on Wednesday, I will monitor everything. If you have a problem, just email me. I hope there's no problem in the middle of the quiz. So see you on Monday then, everyone. Have a good day. Have a good evening. You can also
Thank you, ma'am.
See you, ma'am.